But thank you all so much. I'm really excited to have this opportunity to talk to you all about really a topic that involves organometallic chemistry that has been really near and dear to me for quite a long time now. And so I want to give sort of an overview for you about the topic of catalytic cycloadditions, particularly where and how we can use transition metal compounds to really direct this reactivity in really exciting and cool new ways. So I'm just going to go ahead and dive in. And briefly, this may be a topic that you have some familiarity with from other courses, but just to kind of center ourselves and give you a bit of an idea of the types of cycloadditions I'd like to talk about today is first and foremost, what is a cycloaddition? And as sometimes is the case in chemistry and sometimes is the opposite case. Sometimes the names we give things make it very clear what we're probably talking about. But a cycloaddition is formally defined as two or more separate pi systems where a ring is formed and the total number of pi bonds decreases and the number of sigma bonds increases. So I think of this as we're trading pi for sigma. And in the process of this, as the cyclo part of the name confers, is that a cyclic structure is formed when we do this. And really one of the reasons I have become really drawn to this particular area is there's a lot of aspects of atom economy that make cycloaddition processes really attractive from a complex molecule construction perspective. As you can, it embodies a lot of these ideas of convergent syntheses. And in many cases, you're able to set and construct multiple stereocenters in a single synthetic step, which can be a really great, is a really great idea when we're trying to design syntheses. And so when we are talking about labeling different types of cycloadditions, we generally use the nomenclature of M plus N plus O, where each of these letters designates the number of atoms that each pi component is providing. And so we'll see examples of 2 plus 2 plus 1s, making 5-membered rings, 4 plus 2s making 6-membered rings, as well as 2 plus 2 plus 2s, some of my favorite reactions, making those 6-membered rings, even 4-membered rings from 4 plus 4s, and probably with a lot of biases, my favorite area is making those 4-membered rings in 2 plus 2s. You know, being a square myself, I have great love for other squares, both chemically and in people. So if you feel similarly, thank you for being on Team Square. But also one of the other things that I think we may have some prior experience with in the area of cycloadditions is in the principles of orbital symmetry rules. And this really comes from when we approach this from a much more fundamental organic chemistry perspective. I think many of us may have learned this in other classes, is the ideas of how orbital symmetry can be used to rationalize thermally allowed versus thermally forbidden, and photochemically forbidden and photochemically allowed cycloadditions. And this is really beautiful, elegant work coming from Woodward and Hoffman. This is where the Woodward-Hoffman rules actually come from. And really exciting principles that come out of there. But one of the reasons that I really love the bridging of this fundamental physical organic viewpoint with organometallic chemistry is when you bring in transition metals with all their glorious d electrons, they bust up these rules in a really significant way. And so this actually fundamentally can change what we can consider to be allowable, either photochemically or thermally, because we're engaging these d orbitals that allow different coordination modes. It also allows things to break from synchronicity, so we can actually have much more stepwise processes, which allow for these termolecular processes to occur. We don't have the same entropic barriers present because we have pre-coordination, pre-association of all of those components, which significantly helps certain types of reactions happen. And one of the really exciting aspects that can be governed when we invoke coordination compounds is that we can also include additional supporting chelating ligands or even monodentate ligands. And this can have a really dramatic impact on how the regio and as well as stereoselectivity comes into play. And this is where you maybe lose the stereospecificity that comes along with these orbital symmetry rules in either photochemical or thermal cycloadditions. You can actually use in metal systems the ligand. It can be a catalyst controlled stereoselectivity, which is really advantageous from a synthetic point of view. So I want to provide, before we dive into what I've just chosen as a selection of different types of these cycloadditions that use transition metals, I want to provide a list of general resources that I think are a really great starting point if you're interested in further reading on the general subject of transition metal catalyzed cycloadditions. Some of these examples are going to be catalytic, and many may also be stoichiometric. And so I just want to share these resources with you, as well as give a bit of a highlight out to some of the folks who are some of the pioneers in this area as they're referenced in here. So this is Peter Boldhart, this is Paul Winder, this is Neil Short, and this is Mark Loutons. Just to put some faces to some names for us here. Okay, so the first area of cycloadditions I want to get into here is the Possumcon reaction. And so again, here are a few references if you're interested in learning, doing some subsequent reading about this area. This is a really interesting reaction from a synthetic point of view, but also from a mechanistic point of view. And so this is a 2 + 2 + 1, so an alkyne, alkene, and carbon monoxide. Those are our 2, 2, and 1 components that come together. And this can be used to really wonderful success to make cyclopentenones. Some of the typical catalysts are I would say the most common and some of the earliest are cobalt octocarbonyl, and also there are a variety of rhodium-based catalysts that can be used here. And typically, some of the most common procedures do require the use of CO pressure, and so sometimes this is 1 atmosphere, and many cases though an excess or an increased atmospheric pressure of CO is required. But there are methodologies that allow for CO surrogates to be used, so it slowly releases there. And it's known that certain Lewis basic promoters can be used to increase the reaction rate, mostly by favoring CO dissociation. And if we take a look at the proposed mechanisms if we take the viewpoint of just the cobalt octocarbonyl, this is just a really cool organometallic compound just to think about in terms of electronic structure and coordination to begin with. But really, what is believed to occur in this type of process is that initially there needs to be a dissociation of carbon monoxide. And so this can be sometimes a barrier to entry here, and initial coordination of one equivalent of an alkyne. And this cyclopropanation activation allows then for again, a ligand exchange of another CO for the alkene component, which then undergoes subsequent and favored migratory insertion. And now this is sort of where the CO pressure can be really important, because there needs to be a sufficient amount of CO, because we do need that to serve as a migratory insertion agent so that we can form that cobalt acyl, which then undergoes the 5-membered ring forming reductive elimination, and then subsequent coordination of that alkyne component, allowing that cycle to be regenerated and producing and liberating that cyclopentenone product. And so this is sort of an example where you need to have a system that is relatively flexible, such that CO can dissociate to allow the required pi components to coordinate and insert. But you also need a system that is still saturated enough in CO such that you get the desired insertion and prevent catalyst decomposition in many of those cases. And one of my favorite recent examples, and I'm sorry this is so blurry because this is a screenshot taken from the paper because I was, yes, too lazy to draw those structures myself. But a really nice example that I wanted to take an opportunity to just highlight quickly of using a Possumcon reaction, even in complex molecule synthesis, comes from the Reisman group in 2016 on their route to making ryanodol and its analogs in really a very efficient way. And one of the central parts of their retrosynthetic analysis is recognizing that the required 5-membered ring that's present in all of those molecules can be installed using a Possumcon reaction. And so they intentionally are able to build a tethered alkyne and alkene, and then that cyclopentenone is really beautifully, I think, translated into the correct positioning of all of the other functionality that's required in here through some hydration oxidation sequences. And so really exciting application of that particular type of cycloaddition in complex molecule synthesis, and really I think points to the unique ability of even these types of processes to be applied on molecules that have more exciting functionality than just generic alkenes and alkynes. And so in other ways that we can think about forming 5-membered rings via 2+2+1s, I wanted to highlight some recent chemistry coming out of the Tonks group at University of Minnesota, which they showed that titanium amido pre-catalyst is able to, using multiple equivalents of symmetric alkynes and these azo compounds, allows for the essentially quantitative synthesis of perols. And previously this chemistry was really only hinted at in stoichiometric reactions, but the formation of these titanium amidos really allows this process to become catalytic. And if we take a look at their proposed mechanism here, is we enter into this through a diazine disproportionation reaction with titanium-4. And this actually is what enables the entry point here and allows this process to turn over through the synthesis of these titanium-4 amidos. And it's from this titanium-4 amido that a 2+2 cycloaddition to form these titanocycles allows then for subsequent coordination of the second equivalent of alkyne and migratory insertion. And that forms this titanium 6-membered metallocycle. And this is where favorable reductive elimination occurs, forming that perol 5-membered ring and regenerating titanium-2. And this is what engages with that diazine, that disproportionation process to re-enter that titanium-4 amido. So really, really cool way of using these diazines as a single atom component for 2+2+1s. They subsequently also were able to extend this to using vanadium, and this sort of ups the coordination chemistry a little bit through the usage of these bis amido precursors. And again, very similarly is able to undergo that 2+2, making the vanadium vanadicycles, migratory insertion, formation of that 6-membered metallocycle, reductive elimination is what prompts this. But again, here, the product of that reductive elimination is a mono amido vanadium chloride, and this is what undergoes then that disproportionation reaction with the diazine, excuse me. Okay. Other ways that the substrate scope here can be slightly changed is some chemistry coming from the Buchwald group from the mid-90s that I think might not be exactly what everyone thinks of when they first think of the chemistry from that group, but the usage of these titanium sandwich complexes to promote intramolecular 2+2+1s using, again here, 15 atmospheres of CO at elevated temperatures. And so this was actually, the proposed mechanisms here is very, again, reminiscent of Possumcon type of chemistry, as is maybe unsurprising, but being able to use titanium in its in its role as an activator of alkynes. And so this again, selectively, first, the titanium selectively engages first with that alkynyl component, and then due to the proximity of the tethered alkene, migratory insertion and CO insertion forms that 6-membered titanium acyl compound, which can then undergo reductive elimination under these reaction conditions. So really exciting chemistry there. And I just want to share one more example in the area of 5-membered ring synthesis, and that's basically almost a direct analog, moving from titanium to a rhodium complex using S-binap as a chiral controlling element that enables also the atmospheric pressure of CO to be reduced down to only 1 atmosphere. Very similar mechanistically, except because when we move to a rhodium system, these reduced rhodium compounds are much more prone to initially form a chelate with that bidentate substrate. So coordination of both the alkyne and the alkene. And then that rhodium-1 subsequently undergoes a favored oxidative cyclization, where the rhodium is oxidized to rhodium-3, and that forms that carbon-carbon bond that forms the first part of that 5-membered ring. And then subsequent migratory insertion of CO and reductive elimination forms that 5-membered ring. So it's two kind of contrasting mechanisms that essentially get to almost the same intermediate, but you'll notice a slight difference in the preference of rhodium versus titanium to undergo that regioselectivity of migratory insertion in those cases. Okay, so now we've seen how to make some 5-membered rings via transition metal mediated cycloadditions. Potentially what I think maybe a broader audience's favorite cycloaddition is probably a 4+2, probably some of the first cycloadditions that we encounter in our chemical educations. But if we take a look and deviate slightly from what we typically think about a 4+2, where we have a diene and a dienophile coming together, making a cyclohexene product. This report from Garrett and coworkers indicated that this methyl sorbate, so as well as butadiene, so 2 dienes that we may commonly think of as could be competent in a thermal 4+2. When this is just heated to 135 degrees Celsius, they actually observe pretty good selectivity where that methyl sorbate is functioning as the diene component, whereas butadiene is serving as the dienophile here, which is to me looks a bit like an inverse demand type of Diels-Alder process there. And this is when this is conducted in a stoichiometric, so it's not messing with the stoichiometry to favor this, which is sort of an interesting play on this. And I think more than anything just signals that butadiene is actually, even though we use it frequently as the example for 4+2 cycloadditions, is actually a pretty crummy diene. So I think that's likely the source of that regioselectivity or chemoselectivity that we're seeing there. But there is a small amount of that inverse product where the butadiene is serving as that diene component, and that proximal alkene that I've coded pink here is serving as the dienophile, likely to preserve that conjugation of the methyl sorbate. But they found that using a catalytic amount of a nickel-2 ACAC salt and activating that with triethyl aluminum, which presumably is serving simply as a reducing agent for the nickel-2 in the presence of triphenylphosphine to support that reduced nickel that is produced. They observe now much better selectivity where butadiene now serves as the diene component and the methyl sorbate serving as the dienophile, again preserving that conjugation of the methyl sorbate, utilizing that distal alkene as the dienophile in that, and very good yield. And one of the things that you have to really comb through this paper and read all the footnotes, because this 2-to-1 stereoselectivity that's observed at the end of the reaction is actually, they report is not reflective of the actual bond forming processes that the nickel is participating in. This is actually a thermal isomerization to presumably the more thermodynamically favored trans product, but initially formed from the nickel catalysis is predominantly that cis isomer. And so when we think about mechanistically how or why that might be occurring, it's believed that the butadiene, it results as the diene component on this 4+2 because this is a much better ligand for nickel 0, for reduced nickel, than the methyl sorbate is. And then this engages in a coordinated fashion. There is also potential bidenticity of this methyl sorbate as well, either through the other alkene, but also potentially maybe, though I would probably not think so, through that methyl ester. And then nickel 0, similarly to what we saw for rhodium 1, can undergo this oxidative cyclization. And when that occurs, the necessary carbon-carbon bond forming step forges this carbon-carbon bond. And this forms a nickel allyl species here. And it's this likely slippage between nickel, excuse me, did I say nickel 1? It's not nickel 1. It's very unlikely for this to be nickel 1. It's probably nickel 2. Slippage of that nickel allyl, either between in this position next to the ester or in the conjugate position here. And really the leading hypothesis is that when this nickel allyl exists in this resonance structure here, it's likely that when this process occurs, as the nickel metallocycle, where these two substituents that are vicinal to each other are cis, it's likely that reductive elimination is simply faster from this resonance structure, or from this isomer, and that's why we observe the observed cis stereochemistry in the product is formed, versus during this isomerization, the trans isomer is likely just more stable and less prone to undergo the carbon-carbon reductive elimination step. And so that is, the sort of the leading hypothesis coming out of this work, and explaining. I think we might, in other ways, think that the trans isomer would be much more likely to be preferred, but coming out of that reductive elimination would be the stereodetermining step in that process. Okay. Other 4+2s can utilize components similar to thermal 4+2s that do not use transition metals, and using a tethered diene with an alkyne to make these non-conjugated hexadienes. And this is a really interesting process here, again, using nickel 0 pre-catalyst. But one of the things I wanted to highlight that really I thought was the most interesting thing, to me at least, that came out of this was the dependence of the ratio of the nickel pre-catalyst source with the phosphite ligand that's used. And so when there's a 1-to-1 ratio between nickel and phosphite, it's actually this hydrovinylation product that is the major product formed. And when the ratio of nickel to phosphite is 1-to-3, so a slight excess of phosphite relative to nickel, that's actually where the 4+2 cycloaddition product is the preferred product. And then further increasing that ratio of nickel to phosphite essentially shuts down the reactivity altogether. And so I think if we think about this from a mechanistic point of view, we can understand and rationalize these processes. And again, initial coordination of that nickel 0 with the tethered pi components undergoes then that oxidative cyclization process, making this vinyl nickel allyl. And when we have a low amount of supporting phosphite to occupy this L sub N position, This allows that nickel allele to exist in this form, and because we only have one equivalent of phosphite supporting this nickel, there is an open coordination site, which allows for beta hydrogen elimination to occur, and CH reductive elimination, which is what affords that hydrovinylation product seen here. When we have at least 2 equivalents of phosphite relative to nickel, this can then promote the alternate allele configuration of that nickel allele intermediate. And with a fully saturated nickel at that point, lacking any open coordination sites, this can actually then promote that carbon-carbon bond forming reductive elimination. And that's what affords the 4+2 cycloaddict. And when nickel is overcrowded or has too many phosphite equivalents available, that actually can, the reason that this prevents any either of these products from being formed is that phosphite simply outcompetes even this chelating substrate for the coordination sites on nickel, and so we're unable to get into the required configuration so that oxidative cyclization can even occur. So I particularly enjoy this type of examples because it I think brings together a lot of the fundamental ideas that we know about coordination chemistry and rational ligand design and catalyst design. I think a lot of us probably can sympathize with, we have really awesome ideas on paper and then we go into the lab and try them and it just doesn't work. It doesn't play nicely with us. And so it's I think especially gratifying to be able to find examples such as this that really do make a lot of sense mechanistically with what our hypothesis would be and those rational design elements too. And then in another example of 4+2 before we go on to the 2+2+2s, I just wanted to add in a really different way that transition metals have made a significant impact in the field of 4+2 cycloadditions. And so I'm highlighting probably one of the earliest examples of this chemistry, and maybe some of you might not even be familiar anymore with this type of functionality, these oxazolidinones. Even I'm forgetting the term sometimes. These oxazolidinones. This was a really important when these bear chiral centers at this position derived from amino alcohols. This was a really important advancement that was made by the group of Dave Evans in enantioselective aldol chemistry. And this is a really important step forward in that field of asymmetric enantioselective reactions. But really, I really appreciate and admire this chemistry because in this particular case, this was a breakthrough because this auxiliary, which had been used, in all of the aldol chemistry, now no longer has to serve as the chiral control element, and in bringing these elements of these types of auxiliaries is really here to help to lock the configuration of the dienophile in these 4+2s. And now by merging and using transition metals such as copper-2 with these chiral box ligands, bis-oxazole ligands, which now bear that chirality, this actually goes away from a chiral auxiliary approach, which would be a stoichiometric control element for enantioselective reactions, to a catalytic enantioselective transformations, where you can actually impact that the enantioselectivity by choice of catalytic amounts of ligand. And so while this might not look like the most synthetically applicable type of transformation, I think from a conceptual standpoint, this was really, really innovative and really groundbreaking and really moved things in a substantial direction. And so I'm pulling this figure out of an ACHEMRES from 2000 article, which shows that stereochemical modeling here, but this was actually developed in the early 1990s. And one of the really exciting things about this is it shows that we don't necessarily have to engage transition metals in a way that they need to transition. And so where the electrons from the metal need to engage with the ligands, the pi components that end up in those cyclic products, they can actually be used as a way to bring together these components and provide a chiral environment for the bond forming processes. And that's exactly what copper-2 serves as here. It's more or less serving as an exceptionally useful Lewis acid, and it brings along with it this chirality. And really, you can see here, this is sometimes a little bit difficult. This is just the copper-2 triflate with some solvent molecules, I think, around it. That's the aqua. But when we actually observe the selective coordination of that unsaturated oxazolidinone, you can see the preferential bidentate binding there, the locking of that due to the fact that we have that amide bond in here. And now that C2 symmetry of the bisoxazole chiral ligand essentially prevents formation of the 4+2 adduct from the C phase and prefers it from the Ray phase. Again, I think that's really is exciting to me because I really appreciate the beauty of these C2 symmetric types of ligands, and how, again, not all of our experiments are fully rationalized maybe ahead of time, but this kind of brings together a lot of those really wonderful design elements that we can think of when we're talking about using transition metals as ligand holders as well. And so with that, I want to sort of move forward from 4+2 cycloadditions into 2+2+2s. And so I also want to take a moment to make sure if there are any questions that people could ask them as I go. Feel free to interrupt me. When given the floor and opportunity, I will speak for like forever without breathing. So please, please take advantage of the fact that we can certainly pause for questions if you have them as we're going. Okay. So another really exciting area in six-membered ring synthesis from a cycloaddition perspective is bringing together 3 pi components. And from an entropic point of view, this shouldn't be very favorable. This should be really uphill in terms of the entropy of bringing together 3 components all at the same time. And I think this is really where the use of transition metals is revolutionary, because you overcome those entropic costs by pre-associating the components together, and in many cases having them pre-tethered. And so here's an early example of utilizing this chemistry in complex molecule synthesis. So the Voldhart group demonstrated the use of a cobalt pre-catalyst as a way to actually construct the benzene ring of estrone. And I think I particularly really love these types of examples, because I think when we're approaching complex molecule synthesis, I don't know that we always think of, there's an aromatic ring in my compound, I'm going to make it from scratch. I think we often think of aromatic rings as pre-assembled units that we're going to come and probably decorate and utilize those units from that perspective. And so they were able to kind of leverage the synthesis of that benzene ring to also propel the formation of the conjoined 6-membered ring as well through an expansion of that cyclobutane. But not only can benzene rings be formed via 2+2+2s, but we can also have pyridine synthesis in this type of manner. And this is really an important avenue to try and have new methodologies developed, because of the extreme prevalence of nitrogen heterocycles in pharmaceutical agents. And so ways of making functionalized pyridines especially, and because these can be used as precursors to the most common nitrogen heterocycle pyridines, if we can actually prepare them via first through their pyridines, is really pretty exceptional. And so the Rovas group in the early 2010s, developed this idea that they could use these unsaturated pivoyl oxime esters as the 4-carbon component of a 4+2 using rhodium catalysis. And if we just take a look at mechanistically, again, I'm shamelessly stealing this from their manuscript because this is a really well-detailed mechanistic study that they performed here. But essentially, the rhodium compound here does more or less what we would think rhodium will serve to do in these types of processes. And so initially there's this coordination of that rhodium precursor. It's at rhodium 3, unlike in many of our other cases where we're starting with the reduced rhodium compound. This can then undergo a loss of acetate, and this really is one of the important roles here, is that getting into a cationic rhodium center that allows for olefin coordination, subsequent insertion here. And this is really one of the important advancements here, is that in their approach, this undergoes selective, with very good regioselectivity for the insertion of that alkene, which puts the ester group adjacent to the rhodium, which in other previous methods was a significant difficulty. And then a few more proton transfers or deprotonations here allows us to get to that rhodocycle, which is really the key part here. And you'll probably, hopefully picking up on a theme here, in that a reductive elimination tends to be a fairly common way for these cycles to occur. But unlike in the other cases where reductive elimination is that the final cyclic bond forming step, this is not a reductive elimination. This is actually more a insertion type of process here. And we throughout the process of this don't really change until we get to the rhodium hydride here, anything about the rhodium center. And so I like this example also because the electronic changes of rhodium is not really what's compelling or pushing forward the 6-membered ring formation like we saw in many of those other examples. And a lot of the support for their mechanistic proposal here comes from their deuterium studies, which I won't go into in depth, but this paper does it's a beautiful job of explaining a lot of their excellent mechanistic work that went into this. And then another example I just want to highlight, utilizing iron as the metal pre-catalyst for a 2+2+2 making pyridines, comes from the Louis group at University of Utah, which actually uses nitriles as a pi component, which is a really nice utilization of that type of functionality. And so we're able to access some really nice pyridine scaffolds using this. And this here, rather than using a predefined metal precursor, is an example of being able to use a very simple iron 2 salt along with a chelating ligand, such as these pyridine dialdamines, through the condensation of the aldehyde there, and then using a small amount of zinc as a activator in these cases, allowing this reactivity to go forward.
Can I ask about the
Sure.
Rhodus example? Yeah, why is that called 2+2+2 and not 4+2?
That's an excellent example. And this is probably more appropriately, you're right, I think I should probably put this in the 4+2 because of that conjugation here. And that is probably my error rather than the author's error of calling this a 2+2. But I'm actually not sure if they call this a 2+2+2 or if they call this a 4+2. But I agree. I think you're right. that it's more appropriate probably to call this a 4+2.
Thanks.
Thank you. So yes, I should change my slides. Okay, and so here's an example of a 2+2+2 ene, where we have a tethered alkyne and alkene with an external alkyne as the third 2 atom component. And really what I want to just highlight from here is this undergoes basically, hopefully at this point in this presentation, the exact mechanism that you're probably thinking that rhodium 1 is going to engage with this this ene oxidative cyclization, coordination, insertion, reject elimination. Yep. But really one of the interesting things that came out of this study, I thought, was the impact of the chiral ligand here. So this was an advancement also because of the enantioselectivity obtained in this, but the ability of them to utilize these chiral bidentate phosphines as a way to not only see an impact on the regioselectivity between the insertion of this alkyne component, but also on the enantioselectivity. And so one of the sort of 2 sets of comparisons that they're able to make is that by the inclusion of more sterically bulky groups, they tended to see an increase in the regioselectivity, indicating that regioselectivity was predominantly determined by the steric clashing of the substituents on this alkyne. But then also that the incorporation of electron withdrawing groups, making these ligands more pi acidic, that actually increased the enantioselectivity. And so from a mechanistic standpoint, I think increasing enantioselectivity along with electronic factors of the ligands is probably not the first place that I think most of us come to in our understanding of asymmetric catalysis. I think a lot of times we think about, the energy differences between the diastereomeric transition or enantiose transition states. And I think a lot of times that I, at least, I'll speak for myself only, I at least think of that mostly as a steric controlling factor. And that might just be from a poor educational learning for myself. But I really like this example because it kind of emphasizes what we ought to take into consideration is that electronic effects in the polarization of those transition states can also be used as a factor to enhance enantioselectivity. And that's what they believe is happening here, is that more polarized transition state, by using this more pi acidic type of ligand, kind of allows them to not only maximize regioselectivity through the incorporation of these bulky aryl groups on the phosphine proximal to the metal center, but also achieve really excellent enantioselectivities through the incorporation of changing this into pyridines on the backbone there too. Okay, and so this slide is out of order because this is from the historical perspective, so apologies. In your brains, rewind like 5 minutes, but I like to include this because I still think this is a really amazing example of the power of organometallic chemistry to do these types of cycloaddition. And that's actually an alkyne trimerization, which I think since 1948, we've all seen many examples of alkyne trimerizations. This is many catalysts are able to promote this. But at the time, this was really revolutionary, and that 3 equivalents of propargyl alcohol were able to come together to make benzenes. Now, this did not have excellent regio control by any way, shape, or form, but really served as an early example of the ability of reduced metal nickel centers to pre-associate, undergo these oxidative cyclizations, insertions, and then metallocycle formations, followed by reject elimination to make benzene rings. And so wanted to mostly provide this as a historical perspective. There's been many examples of alkyne trimerization in the literature since 1948. Okay, so let's think about some larger ring formations. And I want to make sure how I'm doing. Yes.
And maybe this is more of just like looking for your opinion on something, but the last slide that you showed, like how useful do you really think reactivity like this is, as opposed to just taking, you know, an arene, which are like pretty ubiquitous starting materials, and functionalizing it the way you want, rather than doing something like this where regioselectivity is going to be really hard to control, using different functional groups in your alkynes, like then you're, you know, how do you really put things where you want on the ring? Do you think that this has a time and a place of synthetic utility, or it's really just interesting reactivity?
Yeah, that's a great question. I think and almost a philosophical one, right? And I guess I kind of come from the standpoint of I love a lot of this chemistry and science, and a lot of chemistry, even outside of cycloadditions, because it kind of touches a place in my brain of, wow, that's really, really cool. I didn't know we could do that, which admittedly might not have a lot of real world utility or applicability, other than like it got somebody like me interested in science. Which allows me to come here and talk to all of you today, which is really, really cool. But I do think there is also a time and place where you're absolutely correct that there are a plethora of arene building blocks available to us. And I think, though, we have gotten here from a place where, yes, lots of arene building blocks are readily available, commercially available. But when we think about kind of ultimately, where do those building blocks come from? Many of them are ultimately derived from petrochemicals. And while I don't know that I believe that there's actually something fundamentally wrong with us making usage of a commodity availability that we have now, I think as we continue to learn more and more about chemistry, I think we can use what we understand about these types of reaction pathways to lessen our dependence on non-renewable feedstock sources. And so I kind of think of it as this is, yeah, an academic exercise in thought, but also I think can be used as a way to challenge our creativity and our innovation, to think about, well, what if, you know, imagine a day where like no more benzene, just gone. It's illegal or whatever, or I don't know. A meteor passes by Earth and all benzene catches on fire. I don't know, pick whatever fun sci-fi scenario works for you. And then it sort of like, it puts us in that place of like, okay, yeah, like it'd be great if we had other ways to make those. And maybe there's ones that you know are much more difficult to prepare in other ways. So by making the aromatic ring while we do this, I think can have some benefits in some scenarios, though. But you're absolutely right. This original report it's not very useful in and of itself. But I think there has been some developments there that address some of the regio controls.
But certainly,
sorry, that was like a really long answer.
No, that's great, Valerie. But also, this is like the same underlying reactivity showed in the Volhart example, where it's a fairly clear and compelling example. So I think in cases where you tether two of the components together, you don't have to wrestle as much with the regio control.
Right. Yeah. Okay. So if we think about making some larger ring sizes, we can start thinking about engaging those diene components with other dienes in order to make 8-membered rings via 4+4s. And so this is sort of something that I think was known in the literature even prior to the 1980s, but that butadiene will dimerize to make 1,5-octadiene, but also can undergo self 4+2s to make vinyl cyclohexene. Similarly, this is sort of a thermal byproduct, or the thermal major product of sort of the idealized 4+2 substrates of butadiene and ethylene. Actually, butadiene tends to prefer to dimerize with itself. But the utilization of a catalytic amount of nickel cod, so a nickel zero source, does in fact start to make more of that 4+4 adduct. And using an electronically biased diene, now using nickel, now the preferred product, the major product, is actually this trans 1,2 diester cyclooctadiene. And this, I think I have maybe some mechanisms here, or no, but well, yeah. So we can understand if we just think about this from a butadiene standpoint, and then you can kind of translate onto the inclusion of the esters at these terminal positions, I think is somewhat easier to see. But this mechanistic work coming from the late 1980s from Wilkie. Again, unsurprisingly, we've seen this a few times now, but nickel, reduced nickel coordinates butadiene, makes these really beautiful butadiene compounds, and subsequent coordination of another equivalent of butadiene, this can undergo oxidative cyclization. And we can think about these metallocycles in three fairly different ways. And the first is in this eta-1, eta-3 anti nickel metallocycle allele. And from this, we can kind of envision slippage to this internal allele position and reduct elimination, generating that vinyl cyclohexene product. But it's actually when we get to the bis eta-3 syn or bis eta-3 anti-nickel allele metallocycles. My brain always, I see everything as a metallocycle, probably even when it's not, but that's, again, my biases creep in there. But we'll look at this from the syn perspective. When we envision that as the both internal allyl nickel species, it's from this structure that likely a reduct elimination forming the cyclobutane forms. But because this is a syn relationship of these two vinyl groups, this really perfectly sets up this for a pretty rapid and promoted through the release of ring strain of that cyclobutane 3,3 ring opening to form the octadiene. Alternatively, from the bis eta-3 anti, we can get slippage to the terminal ends of those alleles, and then reduct elimination directly forms the cyclooctadiene. And so it's fairly challenging to actually parse out the two different pathways here, because under the reaction conditions, this is going to be fairly rapid and irreversible. So trapping this can be quite difficult under those cases. Okay, and so in moving forward with this, where previously there had been a lot of mixtures and controlling this using a nickel catalyst, in the 1980s, Tom Deek actually, and so Tom is not the first name, it's last name, Tom Deek and co-workers reported that they could use this iron 2 salt precatalyst that's supported by this alpha diimine ligand chelate, and activating that with probably one of my favorite activating agents, which is magnesium butadiene. If you've never worked with magnesium butadiene before, I strongly recommend it. It's really nice, and it kind of blows your mind as you're like taking magnesium metal and you put it into a bomb with butadiene, and this like really, you have some solvents are involved, but then you get this like gray powder out, and it's this beautiful reducing agent, and that's used as an activating agent, presumably to access a reduced iron metal, which engages in this 4+2 selectively to form the octadiene, though again, it's not entirely clear if this initially forms the bis vinyl cyclobutane, and then that undergoes a thermal 3,3 to access the cod. And then further improved chemoselectivity, essentially completely removing that vinyl cyclohexene, was achieved by Ritter and co-workers in 2016. Using a single component precatalyst rather than an activating strategy. There, really, really cool chemistry. And so this is when the part of the program where I'm going to shamelessly plug things that are directly connected to me. And this is in the area of 2+2s. And so what if we had catalysts that on purpose were making those 4-membered rings? And so really trying to find a way that would preferentially make the required 5-membered metallocycles, and then forcing that really highly directional CC bond forming reductylation to form that strained cyclobutane would be a really interesting perspective on how to do that. And so the Chiral group reported in 2006. The first reports from the group were using these tethered diallylamines mostly, and these reduced iron compounds supported by pyridine diimine chelates as a way to form these cyclobutanes in very good yields, and in many cases, depending on the substituents on the nitrogen, very rapidly. And then in 2011, they were reported, again, I think a lot of times, and I am guilty of this when I start to explain from the first time 4+2 cycloadditions thermally, we use the most generic components of butadiene and ethylene, and we say, oh yes, this will make cyclohexene, which is a lie. Like I mentioned, butadiene tends to dimerize to make vinyl cyclohexene rather than this cross dimerization process. But really sort of an interesting turn of events, using a slightly altered by the substituents on these aryl rings, a similar reduced iron pyridine diimine catalyst, highly selective cross dimerization for the formation of vinyl cyclobutane was observed. And this catalysis is a little bit slower than previously, but still really excellent regioselectivity. And this is actually, this is some self biography here. This is one of the papers that I read when I was actually a graduate student. And this was really a turning point where I said, I want to go learn about this, and I want to learn about these magic catalysts, and I want to see what else maybe I can help see what they can do. And so from a mechanistic perspective, this has some really interesting insights that the group was able to make, in that I think when we, I'm drawing the spectroscopically consistent electronic structure of this pre-catalyst, whereas we may think of it as it's formally could be iron 0, but spectroscopically we understand it better as an iron 1 high spin center that's antiferromagnetically coupled to a singly reduced radical anion pyridine diimine chelate. So it's this really interesting antiferromagnetic coupling. This compound has a lot of diamagnetic properties to it, which kind of blows your mind when you go take an NMR of it. But this can, they were able to actually isolate and crystallographically characterize this diene complex, and this undergoes oxidative cyclization to form an iron 3 intermediate spin that still has that coupling to the ligand. And it's from this iron 3 metallocycle that selective carbon-carbon bond forming reductylamination occurs. And what's really interesting about these compounds is the precursor is actually an iron nitrogen compound. And in the presence of these olefin compounds, the dinitrogen is displaced. But at the end of catalysis, the dinitrogen compound reforms. And when that occurs, you actually change the spectroscopy. And so it's really interesting that the electrons move depending on what types of ligands are coordinated. So really, I was very excited about this from both a bond forming perspective, but also an electronic structure and mechanistic standpoint. And then later contributions contributed to the ability of doing intermolecular cyclobutane dimerization forming processes using, again, a slightly modified iron compounds. And one of the things that was learned from this intermolecular study was that there was two divergent pathways that could be observed. One was carbon-carbon bond forming reductive elimination to form those cyclobutane rings. And that was favored when either the R groups in the back of this pyridine diimine scaffold were large, or substituents on these aryl rings nearer to the iron center were also large. So that steric bulkiness helped to enforce the desired CC carbon bond forming reductive elimination. Alternatively, beta hydrogen elimination, so this is wrong. Beta hydrogen elimination could be preferred when there is ability of open coordination site to happen, and a beta hydrogen elimination, CH reductive elimination to occur. So this is wrong. But we can suppress the CC bond reductive elimination and favor that beta hydrogen elimination to achieve hydrovinylation processes as well, simply by changing the identity of those groups there. So I apologize that even my slides about my own work are wrong. Sorry, folks. I promise the papers are all correct. And then in another example, I just want to bring up very briefly is that analogous cobalt compounds can similarly be used. And the entry point again here is as a cobalt, spectroscopically cobalt-1 reduced center, which is supported by a singly reduced pyridine diimine. And the entry point here is the cobalt nitrogen dinitrogen compound, which is displaced by the diene, the non-conjugated diene substrate. And this actually then enters, we are simply doing sort of square planar ligand substitution reactions here. So we're replacing first the dinitrogen with only one of the alkenes. And then actually when the second alkene coordinates, it displaces one of the arms of the pyridine diimine tridentate chelate, making it a bidentate chelate, and has no change on the oxidation state at the cobalt center. And this is actually pretty important because that's what can allow the oxidative cyclization at the cobalt center. So you have a 2-electron change at the cobalt center, and now cobalt-3 can have that recoordination engagement of that pyridine diimine arm, which again helps to enforce that carbon-carbon reductive elimination and regenerate into this cycle. And so this was a really fun project that I got to work on, in which utilizing room temperature solution EPR allowed us to actually view a lot of these intermediates along the reaction progress, which was really fun and cool way to use spectroscopy. And so I think I'm okay on time, Kiri.
Yeah, no rush. We have, it's an hour-and-a-half class, so
okay,
we've got until 10.
Okay, perfect. And so the last few examples that I wanted to share with everybody sort of brings us more into the modern era. I still have to remind myself that the 1990s were not 10 years ago, but now 30 years ago. I still feel like, yeah, I still feel like the 90s were 10 years ago. And they were not, but bringing us sort of more into the modern era. And I think a lot of what we see now in terms of 4-membered ring 2+2 cycloadditions is actually the photo side of things. And more now people are uncovering and using transition metal compounds as really powerful agents to affect these photo cycloadditions. And so one particular example that I wanted to highlight, the Yoon group from UW-Madison really has a long history that predates even 2016. But I want to highlight this particular example because it utilizes two metals in very different ways, and synergistically is really what allows this catalysis to occur. And so we sort of have seen some elements of this previously, especially you're talking about the 4+2 copper Lewis acid chemistry. And so in this particular example, what they're describing is that these synamyl derivatives that now have, not necessarily, I wouldn't call this an auxiliary here, but this sort of directing group, this chelating group, these orthophenols as part of these groups, this enables that bidentate chelation, and this selectively is engaged by scandium triflate, and that scandium triflate comes along with that chiral control element of these pi box ligands. So again, really sort of connecting back into what we saw previously with the copper bisoxazolines. And this actually serves multiple purposes. Not only does that coordination of that scandium bring along the chirality, that C2 chirality to this, but this serves another really important aspect of this chemistry in that the parent substrate has triplet energies about 50-ish kilocalories per mole. And then upon coordination of the scandium, it lowers those triplet energies by roughly 20 kilocalories. So a really dramatic shift in lowering how difficult it would be to do an excitation, a photosensitization of that complex by Lewis acid coordination. And this is really important because the other catalyst, metal catalyst that's used in this system is ruthenium trisbipyridines, which I don't know that I have to go into lots of detail. I think many of you are probably pretty familiar with RuBiPi and the corresponding iridium types of compounds and their ability to serve as photoredox catalysts, but also they're more and more being used as photosensitizers, and they may have been used as photosensitizers also in previous literature, but mechanistic studies may sort of muddy exactly what its role is all of the time. But this is a really crucial part of the scandium activation here, because the triplet energy of RuBiPi is measured at 46 kilocalories per mole. And so in order to actually activate this alkene component, we have to have a photosensitizer that is strong enough, that has a triplet energy higher than the compound that we'd like to activate using that. And so this serves not only to bring in that chiral environment, but also does that triplet energy lowering process through that coordination as well, so that now we do have a substrate that can be selectively activated by the relatively mild photosensitizer of RuBiPi. And so some really beautiful mechanistic work is also featured in this paper that I really appreciated that the group took the time to include as a way to make cyclobutanes here using some of these substituted butadienes. And so I think this is a really nice way of the different roles that transition metals can play in cycloadditions, particularly when we start to engage them with light as well. And then 2 examples came out in 2020, both by the Schindler group at University of Michigan and the Yoon group. Again, you'll notice here these page numbers. Is this a typo? I know I'm prone to making typos, as I've already demonstrated, but this is actually not a typo. These are back-to-back articles in the same issue of Organic Letters, kind of suggesting that 2 really amazing groups had the same great idea at the same time. I'm sure there was probably some communication at that point, but I, of course, am speculating. And this is where they're utilizing these iridium compounds, and so these are very large, and I didn't redraw them, and I also assume that many of you probably have some pre-existing knowledge about these compounds, but essentially in this particular example, they're using this highly fluorinated iridium compound as a photosensitizer here that selectively activates this aryl ketone component of these compounds and enters that triplet state, and that can engage selectively with a variety of substituted alkenes in order to form oxetanes. And this is a really interesting advancement in the area, because I think probably if we're talking not about organometallic mediated types of cycloadditions, paternobutyl 2+2 photocycloadditions typically is presented hand in hand with 4+2 thermal cycloadditions, and have complicated viewpoints maybe on named reactions that I can save for a different time and place. But I think one of the things that comes out of Well, it's the Paterno-Bucchi reaction. It's a named reaction. That must mean it's perfect and a solved problem. And this actually is not necessarily reflective of reality. And so oxetane forming photo 2+2s can be really limited in terms of the substrate pairings. So being able to use photosensitizers that have tunability in them as a means to activate ketones, not through direct irradiation, does provide the ability to really substantially expand the scope of the types of oxetenes that can be formed. And also by using these types of iridium photosensitizers that are activated using visible light, this similarly makes them much more practically easy to do rather than using stronger or higher energy UV light activation. And in addition to oxetane forming photo 2+2s through photosensitization, the Schindler group also reported last year this really interesting glyoxylate oxine ether compound that they were able to demonstrate that can undergo really selective photosensitization from a slightly different iridium photosensitizer using slightly, but still, visible light activation. And this can selectively activate that carbon-nitrogen bond. And this is actually fairly uncommon because as a pathway for productive bond-forming processes, because when we think about the difference in activating a carbon-nitrogen double bond of an imine versus the carbon-oxygen double bond of an aldehyde or a ketone, an aldehyde or a ketone, there is no substituent on the oxygen. So that excited state exists as it is and can be captured or thermally quenched in a variety of other pathways. But in an imine situation, because the nitrogen does have another substituent, very commonly what has sort of hindered the corresponding aza-Paterno-Bucchi type of reaction development is that there is a very low energy, easy isomerization decay pathway for imines. And so this is actually a really clever way of using an oxine ether tether that not only does have that nitrogen oxygen weak bond that can be cleaved, opened up in the product, but also helps to address and remove the easy isomerization pathway of this reagent. And so this was a really beautiful synthetic methodology development, because I've chosen only one alkene as an example here for regioselectivity purposes, but really the scope of alkenes here is very, very large and extensive. And I largely attribute that to the pretty mild activation mode and selective absorption of that or excitation of that oxine ether component there. So really exciting chemistry there. And so that brings us kind of up to mostly recent dates. I still haven't registered that we are halfway almost through 2021. And so this is my final slide of these cycloaddition notes. But I hopefully what kind of comes out is there are a few pretty common mechanistic pathways that a lot of metal-mediated cycloadditions can occur through. But what I think is really cool and really exciting is that we continue to find new mechanistic pathways that allow us to engage new substrates for new types of sizes of rings. Of course, I'm biased to the four-membered rings, but also in trying to expand how we think about bringing those kind of components together. So yeah, I'm happy to answer any additional questions anybody might have about any of the examples I've shown, and hopefully everyone knows that this was not intended to be a comprehensive collection of all the different types of cycloadditions, but sort of an overview of some of the ones that I personally think are some of the most exciting and identify a lot of the mechanistic themes of these types of reactions.